Okay, beta. So in the last lecture we have covered up to question number 50, and today we'll start with question number 51 and previous year questions from 2012 to 2015 we are going to cover. The first question is, what is lanthanoid contraction, and mention its main consequences. So yes beta, what is lanthanoid contraction? Yes, it is steady decrease in ionic radius. Steady decrease in ionic or atomic radii along the series. That is called lanthanoid contraction. Steady decrease in atomic or ionic radii as among lanthanoids on increasing atomic number. And what is the reason for it? What is the reason? Yes, it is due to imperfect or poor shielding of 4f electrons. And what are its consequences? So first consequences, because there is a steady decrease, so their properties are almost similar. Properties are almost similar, and therefore they are difficult to separate. And second is second and third transition series elements of the same group, elements of corresponding groups are almost of same size. For example, zirconium and hafnium, niobium and tantalum, they have almost similar size. If question is why, then it is due to lanthanoid contraction. And third is, as size decreases along the series, so lanthanum hydroxide is most basic, and along the series basic character decreases, and lutetium hydroxide is weakest base. Next question. Write the balanced ionic equation for the reaction between ferrous sulfate and acidified potassium permanganate solution. So see, potassium permanganate. So ion involved in the redox reaction is MnO4 negative. In acidic medium, MnO4 negative will give Mn2 plus. Just balance this equation first. Add H2O to the side deficient of oxygen. Double number of H plus ion to the opposite side. Now 7 positive on the left side and 2 positive on the right side. So 5 electrons. Then Fe2 plus. In ferrous sulfate, the ion which is oxidized is Fa2 plus. So Fe2 plus is oxidized to Fe3 plus and gain 1 electron. So it is multiplied by 5 to balance the number of electrons gained and lost. So it is MnO4 negative plus 5 Fe 2 plus 8 H plus to give Mn 2 plus 5 Fe 3 plus 4 H2O. So this is the balanced ionic equation of KMnO4. In KMnO4, active ion is MnO4 negative, and in ferrous sulfate, active ion is Fe2 plus. So Fe2 plus is oxidized to Fe3 plus, and MnO4 negative is reduced to Mn2 plus, and this is the balanced equation. Yes. Now next one. Oh, sorry. How would you account for the following? Transition metals exhibit variable oxidation states. Yes, beta. Yes, they exhibit variable oxidation state because reason is in transition elements n-1d and ns orbital energy is almost same. Energy of n-1d and ns orbital is almost same. So both can participate in bonding. This is the reason. Okay, that's why they have variable oxidation states. Second is very easy question. Why zirconium and hafnium have almost identical radii? Just yes, it is due to lanthanoid contraction. Because zirconium is from the second transition series and hafnium from the third transition series of the same of the corresponding group. So due to lanthanoid contraction, they have almost similar or identical radii. Next, why transition elements, metals and their compound act as catalyst? So due to the first, due to the presence of unpaired electrons in partially filled d orbitals, second thing, they can provide surface area for the reaction to take place. They have variable oxidation state. They can form intermediates. They can form complexes. These are the properties which are needed to act as a catalyst. So that's why transition metals and their compounds act as catalysts. Yes, complete the following chemical equations. First is Cr2O7 2 negative. Cr2O7 2 negative. So in acidic medium, Cr2O7 2 negative ion, it gives Cr3 plus. Gives Cr3 plus. So balance the atoms other than hydrogen and oxygen. So chromium is other than hydrogen and oxygen. So 2 chromium on the left side and multiply Cr3 plus by 2. So 2 chromium on the right side. Now add H2O to the side deficient of oxygen and double number of H plus ion to the opposite side. So total 12 positive on the left side and 6 positive on the right side. So add 6 electrons. Now second is Fe2 plus. So obviously Fe2 plus ion gives Fe3 plus. So to balance the charge, just add 1 electron on the right side. And now to balance the electrons on both sides, to cancel out the number of electron gained and lost, we multiply the second equation by 6. So it becomes Cr2O7 2 negative plus 6 Fe2 plus 14 H plus to gives 2 Cr3 plus 6 Fe3 plus and plus 7 H2O. That's it. Second one, CrO4 2 negative. So CrO4 2 negative in acidic medium, it gives Cr2O7 2 negative. Chromate is yellow in color, turns into dichromate, okay, which is orange in color, and just balance it. So 2 chromium is balanced. Now 8 oxygen on the left side, 7 oxygen on the right side. Just add 1 water molecule and double H plus ion to the opposite side. So this is the balanced equation for the second one. Now third, it is MnO4 negative and C2O4 2 negative. So MnO4 1 negative, it gives Mn2 plus. C2O4 2 negative, it gives CO2. So 2 carbon on the left side, just multiplied by 2. Oxygens are also balanced, just add 2 electrons, 2 negative on the left side, so 2 electrons on the right side. Now MnO4 negative to Mn2 plus, add 4 water molecules on the right side because 4 oxygens are deficient on the right side, and double number of H plus ion to the opposite side. Now on the left side there is 7 positive charge, on the right side 2 positive charge. So we add 5 electrons. So just multiply second equation by 5 and first equation by 2 to balance the number of electrons gained and lost. So overall it becomes 2 MnO4 negative, 5 C2O4 2 negative plus 16 H plus 2 Mn2 plus 10 CO2 and 8 H2O. That's it. Now question number 54. Write the balanced chemical equations for the two reactions showing oxidizing nature of potassium permanganate. So see, potassium permanganate, let us take it in acidic medium. So if potassium permanganate in acidic medium, so it will give K2SO4, MnSO4, K2SO4, so 2 MnSO4, so 2, so total 3 SO4 is 3 H2SO4, so add 3 H2O. So now go to the 8, out of 8 oxygen 3 are involved here, so total 5 oxygens. See, this is the molecular equation. Earlier we are writing ionic equation. Now first let us take ferrous sulfate. So ferrous sulfate can be oxidized to Ferric sulfate, ferrous to ferric. So 2 iron, so means I have to write 1 and 1 H2SO4. So to balance these hydrogens, add water. See, 2 iron, okay. Sulfate, total 3. 2 SO4 here, 1 SO4 from H2SO4. So 3, okay. H2O, so add 1. Nascent oxygen, in this way it is balanced. So we multiplied by 5. It become 2 KMnO4, 10 FeSO4, and 5 plus 3, 8 H2SO4, K2SO4, 2 MnSO4, then 5 Fe2SO4 thrice, and 5 is 8 H2O. Just check, is it balanced? Potassium 2, okay. Manganese 2, okay. Iron 10, okay. SO4 10 plus 8, 18. Okay, 5 is 15, 17, 18, okay. Now what is left? 8H2, okay. Oxygen, SO4 we have taken 8 oxygens out of 8 are used in water. That's it. So this is first reaction for oxidizing action, which shows oxidizing nature of potassium permanganate, okay, in which KMnO4 oxidizes ferrous sulfate to ferric sulfate. Second, again same reaction, KMnO4 plus H2SO4 to give potassium sulfate, manganese sulfate plus H2O and nascent oxygen. So 2, 2, and 3, 5. Then let us take H2S. So H2S is oxidized to sulfur along with water. So 1 nascent oxygen, again multiplied by 5. H2S is oxidized to sulfur. Okay. We get 2 potassium permanganate, 5 H2S, 3 H2SO4, then K2SO4, two MnSO4, 5 sulfur, 8 H2O. Okay. So this is the second equation. Now give reason for the following. Transition metals exhibit a wide range of oxidation states. Transition metals exhibit a wide range of oxidation states. So what is the reason? Transition metals exhibit a wide range of oxidation states. Transition metals exhibit a wide range of oxidation state. What is the reason? Same, because there is n-1 d and ns electrons and ns orbitals having same energy, almost same energy. N-1 d and ns orbitals having almost same energy. So they exhibit wide range of oxidation states. Second, cobalt-2 is very stable in aqueous solutions but gets easily oxidized in the presence of strong ligands. Because cobalt-2 plus it is 3d 7 and cobalt 3 plus it is 3d 6 plus electron. So in the presence of strong ligands, it exists as T2J6, that is more stable, and that's why cobalt 2 plus is easily oxidized to cobalt 3 plus in the presence of strong ligands. Next, actinoid exhibit a large variation of oxidation state, greater range of oxidation states, because 5f, 6d and 7s orbitals have almost same energy. So they show wide range of oxidation states. Okay. Okay, beta. I took class tomorrow now. Okay. I have some work. Okay. Okay. So total 5 questions for today. We will continue tomorrow.